Okay, so what in the world does a legendary rock band have to do with a 300-year-old math puzzle? I know, it sounds like a weird setup for a joke, but the answer is actually this huge idea that shapes our world in ways you might not even realize. So, yeah, let's start with the band. When you pick up a university textbook on probability, you're expecting what? A wall of equations, right? But nope, Professor Rick Durrett kicks his off with the Grateful Dead. It's his way of telling us, hey, this isn't just about numbers on a page, it's about life's long, strange trip.
And he actually frames the whole book around his own long, strange trip. Watching the world change like crazy from his first edition back in '89 to today. And that's the perfect setup for what we're about to get into. How, if you wait long enough, even the most random stuff starts to make sense.
So, this whole idea of finding a pattern in the chaos, well, it brings us to this game from way back in the 1700s. On the surface, it's just a coin flip. Super simple, but it's a puzzle that absolutely broke the brains of some of the smartest people back then. It's called the St. Petersburg paradox, and it doesn't seem to make any logical sense.
Okay, picture this. You and me, we're gonna play a game. I flip a coin, it lands on heads, I give you $2. Easy. But if it's tails, we double the stakes and go again. So on the next flip, if it's heads, you get $4. Another tails, we go for 8. See how this works? The pot just keeps doubling. So here's the big question, maybe the infinite dollar question. What's a fair price? How much would you pay me right now for just one shot at this game?
And just look at these numbers. It gets wild, fast. Get heads on the 10th toss, and you're already over $1,000. Get it on the 30th? We're talking more than $1 billion. And in theory, there's no limit. It could just keep doubling and doubling forever. The potential payout is literally infinite. And that is the paradox. See, back in 1713, a mathematician named Nicholas Bernoulli pointed this out. He said, look, the math tells us the value of this game is infinite, but would anyone actually pay an infinite amount to play? No way. Your gut, your common sense tells you it's probably only worth a few bucks, right? So, what gives? Why is there this huge gap between the math and our intuition? All right, to crack this thing open, we gotta grab a couple of key tools from Professor Durrett's book. Think of them as the keys that are gonna unlock not just this little coin game, but the whole idea of randomness itself. First, we've got something called a random variable. Now, that sounds way more complicated than it is. Seriously, don't let the name spook you. It's just a fancy term for assigning a number to a random outcome. So in our game, the random variable is just the payout, the amount of money you could win. Okay, tool number 2 is expected value. The easiest way to think about this is it's the average you'd expect to get if you played a game over and over and over again, like a gazillion times. You just take every possible thing that could happen, multiply it by its probability, and then add all those up. But here's the catch. When you do that for our coin game, the total just keeps climbing. 1 plus 1 plus 1, it goes on forever. And boom, that's where we get that pesky infinite expected value. So you've got this battle, right? Our gut instinct versus the pure math. And that sets the stage perfectly for the real hero of this story, the law of large numbers. This is the big idea. This is what connects that crazy abstract math to what happens in the real world. Here's the thing you've really got to get. Playing the coin game just once, totally unpredictable. Could be $2, could be 2 billion, who knows? But if you play it, say, 1,000 times or 1,000,000 times, suddenly the average payout becomes super, super predictable. It's this amazing shift from short-term chaos to long-term order. And this law, it makes us look at the whole problem differently. We've been asking the wrong question. The question isn't, what's one game worth? Because, like we saw, that leads to infinity. The real question, the better question, is if we're going to play this game a bunch of times, not an infinite number, but a large, real number of times, what's the average game worth? And you know what? When you ask that question, the answer isn't infinite at all. It's actually kind of small. Durrett's text does the math, and it turns out, if you were going to play this game 1,024 times, a fair entry fee per game would be, wait for it, just $10. $10! Not infinity, not some crazy number, just 10. So why so low? I mean, what about the billion-dollar prizes? Well, it's because hitting one of those is so incredibly rare, it's almost impossible. You are way, way, way more likely to win the small amounts. $2, $4, $8.
And over thousands of games, it's those small, common wins that really shape the average. Those giant lottery-style payouts, they're so rare they barely even make a dent in the overall average.
So there you have it. We've cracked a 300-year-old puzzle. But this isn't just some dusty old brain teaser, okay? This idea, this principle, it's one of the foundations of our modern world. And Professor Durrett just nails it when he says, probability is not a spectator sport. This isn't something you just sit and think about. The law of large numbers is a tool. It's something we use to build real, predictable systems in a world that can feel totally chaotic.
Seriously, if you take one thing away from this, let it be this. The law is kind of like a magic trick. It takes one single event, which is completely random, and when you do it enough times, it transforms all that randomness into something stable and reliable. It's literally how we find the signal inside all the noise. And what's cool is, once you get this concept, you start seeing it absolutely everywhere. Think about insurance. They have no clue if you're going to crash your car, but they know with amazing accuracy how many crashes there will be among millions of drivers. Or casinos. They don't know if you'll win the next hand of blackjack, but they know for sure that over millions of hands, the house is going to come out on top. It's the hidden engine behind polling, scientific research, you name it. So just let that sink in for a second. The very same logic that solves a weird coin game from the 1700s is also the reason your insurance premiums are what they are, and it's how we know a new medicine is safe and effective. It's this quiet, powerful force that takes all the randomness of the world and makes it, well, manageable. It creates a world we can actually navigate. So the real question to leave you with is, now that you know what you're looking for, where else do you see it working?